Hi, this lesson is about functions and the domain and range of a function. So before we talk about what a function is, we have to understand what a relation is. So a relation is a rule that defines a relationship between two variables, and we usually call them x and y. It is possible to have more than one y associated with any one value of x in a relation. So an example of a relation is this rule here, y squared equals x. Ordered pairs that satisfy this relation are the ones that you see here in this set. We have 0, 0, 1, negative 1, 1, 1, 4, negative 2, and 4, 2. Notice that we have two examples here of an x value that goes to two different y values. So 1, negative 1, as well as 1, 1. And then we have another 2 to the right for negative 2 and 4, 2. So 4 gets mapped or is associated with two different y values of negative 2 and 2. Okay, so now let's talk about what a function is. A function is a special type of relation. It is a rule that defines a relationship between an independent variable, which again we usually call x, and a dependent variable, which we usually call y, where for every x there is only one value for y. So every x value can only be associated with one y value, not more than one like we had in the previous example. So a function is a type of relation. So here's an example, y equals x squared. Ordered pairs that satisfy that function are negative 1, 1, 0, 0, 1, 1, 2, 4. There's actually infinitely many ordered pairs that satisfy that function, but this is just an example. So for every x value, there's only one y value. Now it is possible for the y values to be repeated. As you see here, I have negative 1, 1 and 1, 1, but that's okay because the 1 is associated with a unique x. So in other words, your x's cannot be repeated, but your y's can. All right, so we're going to determine if the following examples of ordered pairs is either a relation or, more specifically, a function. So we have two examples here, A and B. So let's look at A. A has the set of ordered pairs negative 1, 1 half, negative a half, 1 quarter, 0, 0, 1, negative a half, and 2, negative 1. So none of the x values are repeated. Therefore, you can say that this is a function. So part A here is a function. Now let's look at B. B gives us the coordinates of 0, negative 1, 0, 1, negative 1, negative root 2, negative 1, root 2, 1, negative root 2, and 1, root 2. All right, well here we have to say that this is just a relation, not a function, because there is more than one value for any single x value. And it happens all throughout, right? 0 gets mapped to negative 1 and 1. Negative 1 is associated with negative root 2 and root 2. And then here I gave the last set of ordered pairs as an example. 1, negative root 2, 1, root 2. There are multiple examples of where the x values are repeated in the ordered pairs. Okay, so let's talk about domain and range. So first, let's look at definitions. So the domain of a function. This is the set of all possible values of the independent variable. Again, we usually call that value x, but it doesn't have to be. It's just commonly called x. And the range is the set of all possible values of the dependent variable, which we usually call y. So in other words, y is dependent on what x is. So we want to identify the domain and range of the following sets. So let's look at the set A. So the domain for set A, all you need to do is list all of the x values. So in other words, the first coordinate in each of the following ordered pairs get listed right here, and we use the curly brackets to indicate that it's a set of numbers. And similarly, you do the same thing with the y values. So all of the y coordinates get listed below. And again, we put it in the curly brackets to state the range. So we start with -1 all the way through till we get to 4. And that's our range right here. Okay, so we'll do the same thing with the set below for B. We want to state domain and range. So for B, first we list all of the x coordinates here for domain, and then we list all of the y coordinates here for range. And so you have stated what the domain and range is given those orders. Okay. So domain and range is actually a bit more complicated than what we did above, because really domain and range is the set of all possible values of the x for domain and all possible values of the y for range. So in fact, most functions will have an infinite number of possibilities. So we're going to state domain and range based on the following 3 graphs that I've labeled A, B, and C. So let's state the domain and range of A. A is what we would consider to be a linear equation. So if you were to graph that, that's a straight line, and you see the graph below. So the domain is stated right here, and I used 2 different notations, set builder notation and interval notation. And so their set builder is above and interval is below. Now, because x can be any value, it could be a negative number, a positive number, a 0, it could be a fraction. Whatever you substitute in for x, you get a corresponding value for y. So your domain is a set of all real numbers. So in interval notation, we use this little fancy r here, has like a double line at the beginning. That means the set of all real numbers. And in interval notation, well, you state that as from -infinity to infinity. And you can also see here in the graph that these arrows mean that this graph goes on and on forever in both directions, which means that for every x value along the x-axis to the left and right of this, you would be able to find the corresponding point that goes along with it. So every single x value is accounted for. All right, the same is true for range. Because this graph goes on and on forever, again in both directions, for any y value that you pick along the y-axis, positive, negative, or 0, you'll be able to find the corresponding point on the line. So your range is also all real numbers. And again, it's stated in interval notation and in set builder notation, interval notation and set builder. All right, so let's look at B. This is y equals x squared. This is a quadratic equation. The graph of a quadratic equation is called a parabola, and that's what it looks like right here. So similar to what I explained with lines, your x could be any value. It could be positive, negative, it could be 0. You square it and you get a value for y. So your domain is still all real numbers stated with set builder notation and interval notation. But your range, well, there's a restriction here. Notice that there is nothing on the graph that is below the origin. There's nothing down here. So that means that your y values start from this point and then they go up or get larger from that point forward. So your range is the set of all numbers greater than or equal to 0. And in interval notation, you state it like this with the square bracket, meaning include 0 all the way to infinity. So that's 2 different ways to express the range. All right, so let's go on to C. This is another parabola. This one happens to be facing downward. It's upside down. So again, your x can be anything. It could be positive, negative, 0, fractions, decimals, radicals, anything. So your domain is all real numbers. but your range. Okay, so when we look at the range, notice that these arrows indicate that this parabola goes downward forever and ever, but there's nothing above 4, right? There's nothing above 4. So your range is the set of all real numbers up to and including 4. So the way you state that, the set of all negative real numbers and then all the way from 0 to 4. So the way you state that, it's y is less than or equal to 4, or it's the interval from negative infinity to 4, and you close the bracket. Remember, with interval notation, you always write your interval from smallest to largest. So that's why negative infinity goes first, and then the 4 goes second, and the square bracket means to include the 4. Okay, so when you have a variable or variables in the denominator of a function, it is possible that there is a restriction or an exclusion to the domain, meaning you have to omit it from the domain because you want to avoid anything that would result in you dividing by 0. So zeros in the denominator mean that the function or equation, whatever you're working with, is undefined. So we have a few examples here. We want to determine the values that are excluded from the domain, then state what the domain is. Okay, so here's our first example. Y equals 5 over x. Well, the only time my denominator would be 0 is when x is 0. So x equal to 0 is excluded from the domain. So that answers the first part of the question. Now, what's the domain? So this is the way you state it in set builder notation. My domain is the set of all x such that x is not equal to 0. So what that implies is that any other number is in the domain except 0. So we're only stating what x cannot be equal to, but that means all other real numbers are in the domain. All right, now let's look at number 2. We have y equals 2x over x plus 3. Remember, our concern is the denominator, not the numerator. So I take the denominator and I set it equal to 0, as you see here. And when you solve it, you get x equal to negative 3. Negative 3 is the value that is excluded from the domain, because when x is negative 3, if you plug it into the equation right here, you get 0 in the denominator. Okay, so in terms of domain, you would say that the domain is the set of all x such that x is not equal to negative 3. Again, that means any real number except negative 3 is in the domain. All right, now let's look at the third one. Third one is a little bit more complex. I have y equals 1 over x divided by x squared minus 3x minus 4. Again, don't worry about the numerator. We're focusing on the denominator. So I take the denominator and I set it equal to 0. So this is a quadratic equation. It's factorable. And it factors into x minus 4 and x plus 1. And when you solve each factor for 0, you get x is equal to 4 and x is equal to negative 1. So remember, these are not solutions. These are exclusions or restrictions. So 4 and negative 1 are excluded from the domain. Okay, but when you state the domain, you want to say that the domain is the set of all x such that x is not equal to negative 1 and positive 4. So when you're doing the homework, make sure you're answering the appropriate question. Sometimes you're just being asked what values are excluded from the domain. Sometimes you're just being asked, state what the domain is. And in other cases, they might be asking for both answers, both the exclusion and what the domain is. All right, functional notation. So functional notation is a convenient way of restating y. Y equal to f of x. They mean the same thing. So this one right here does not mean f times x. It is read as f of x, meaning a function of x. Y is a function of x. So I'll show you how we use it, this functional notation. So here's an example. We have given that f of x equals negative 2x plus 5. We want to evaluate f of negative 3 and f of 1. All right, so remember, f of x equal to negative 2x plus 5 is the same as saying y equals negative 2x plus 5. And we just want to evaluate it when x is negative 3, which is what you see here, and when x is 1. All right, so the work is right below. So I have, all right, so I have f of negative 3. That means substitute negative 3 in for x, which I have right here. So it's negative 2 times negative 3 plus 5. So that becomes 6 plus 5. So your answer is 11. It's the answer in the box. Then we go on, plug in 1. So f of 1 means replace the x with 1. So it's negative 2 times 1 plus 5. That's negative 2 plus 5. And your answer is 3. All right, so here's a similar example where we're using functional notation. You're given that g of t is equal to negative t squared plus 3. So a couple of things to mention here is that you don't always have to use f for f of x, and you don't always have to use x as your independent variable. Here, the t is what I would have normally called x in previous examples, and the g of t is like an f of x or the y. So the question is to find the range for the given domain. Remember here, the domain are the t values, and the range are the g of t, which is the same as the y values. All right, so we do that work below. First, I plug in the first value in the domain, g of negative 2. And when you do that, remember that you have a negative outside of the t squared, so that has to remain outside of the negative 2 squared. So you get negative 4 plus 3, and your first result is negative 1. Then you plug in negative 1, same idea. The negative stays outside of the negative 1 squared, so you get negative 1 plus 3. The result is 2. Then you plug in 0, and the result is 3. Then we move on to plugging in the fourth number, which is 1, right here. So again, the negative is on the outside. You square the 1, you get negative 1 plus 3. The answer is 2. And you do the same thing below by plugging in 2. You get negative 4 plus 3. The answer is negative 1. So notice that I have 5 values of the g of t or y, but 2 of them are repeated. I have negative 1 here and negative 1 here, and I have 2 here and 2 here. So when you state the range, it's not necessary for you to repeat values. So you just state all of the unique ones, and you have that the range is negative 1, 2, and 3. So remember, it's okay for the y values to repeat in a function. It's just not okay for you to repeat the x values. Okay, here's another one. This time I've given you a rational function. This is what we consider to be a rational function when you have at least one variable in the denominator. And again, I'm showing you how you don't always have to use f of x. Here I'm using h of w. So w is my independent variable, and my h of w will be my dependent variable. So we want to find the range for these given values of w. So these values of w are basically your domain in this problem. So you plug in each of those numbers, and so that's the work you see here. H of negative 2 means that I have negative 2 squared divided by negative 2 plus 1. So that result is negative 4. So everything that I'm calculating for range will be in a box. Then you plug in 0, and you get 0. Then we have to plug in 1, which is here on the right. So plug in 1, and that's right here. And you get a half. And then you plug in 2, and you get 4/3. So all of these range values or h of w values are unique. So you list them all out, and you get the result right here. So that's your range. Okay, so let me just do one more example where you're your functional notation might be a little bit more abstract. So suppose I have, let's say, f of x equal to x squared minus 3x plus 1, and we want to find f of a. Well, your input doesn't always have to be a number the way we did above. So if I want to find f of a, it's actually as simple as just replacing all of your x's with a. So I get a squared minus 3a plus 1. Now, suppose I use same function. So suppose f of x equals x squared minus 3x plus 1. And I said to find f of a plus h. Well, this time the input is a plus h. So it's a sum of two unknowns, a and h. So f of a plus h, that means that everywhere there's an x in the original function, you replace it with a plus h. So x squared becomes a plus h squared. And minus 3x becomes minus 3 times a plus h. So notice you need the parentheses in order to group the a plus h together. And then the 1 doesn't have a variable, so it stays as 1. Now, in this case, there is work to do because you can FOIL the a plus h squared and you can distribute the negative 3. So when I FOIL a plus h times itself, I get a squared plus 2ah plus h squared minus 3a minus 3h plus 1. Then you look for like terms. There aren't any, so you're done. Okay, so now you're ready to try the homework for this section. Good luck.